Hi guys, welcome back. Today we'll start off a lesson by recapping what we have done in the previous week, right? We're going to use reaction 9.3 to do that. So to look at this reaction, we're going to start off with a carbonyl compound, and through the use of HCN, we end up with this thing called a cyanohydrin. Right? Now, for this reaction, it's an example of a nucleophilic addition reaction. The reason is because first we start off with the carbonyl part. O is a very electronegative atom. It causes this C to be electron deficient. Yep. So we call this N
electrophile.
That's right. And what's going to happen is that it's going to get attacked by a nucleophile. Yep. That is why we call this a nucleophilic reaction. Yep. So Mr. Yap, can you share with me which part gave me the nucleophile?
Right, so it should be the CN minus that is acting as the nucleophile in this case.
So the CN that came from HCN, the CN minus would be acting as a nucleophile.
Yep.
Now, CN minus, right, there is going to be a distinctive feature that makes it a nucleophile. What is that?
Right, so a CN minus is a negatively charged ion. Right, it's electron rich. It has lone pairs available for donation. Hence, it's able to act as a nucleophile. Okay, so lone pairs. So in terms of the CN minus, right, where is the lone pair going to be on? I noticed that I think there are two, each C and the N all have their own lone pairs. Right. So which is the one that is going to be more available for donation? Right. So the one that is more available for donation will be the lone pair on the carbon, because carbon is less electronegative than nitrogen. So being less electronegative, it will be more willing to give up its electrons for donation.
That's right. Yep. So this is going to do a nucleophilic attack on the electron-deficient carbon atom, and it causes this CO bond to break. Okay, right. So in this case over here, what we are doing is actually a breakage of the C double bond O, right? One of the weaker bonds, which is the pi bond, is going to break, right? And as a result, we are going to add two things across them. And as we saw that the CN is performing the nucleophilic attack, the CN is going to be bonded to the C, and the remaining H from the HCN, right, will be bonded to the O. And as a result, you're going to get an alcohol and a nitrile group on the final organic product. Yep. This is what we call a cyanohydrin, right? Now, let's start off with the mechanism. So I'm going to use a new page to do that. If you have some space, you can do that together with me. Now, the first things first, when I look at any mechanism, is always to write down the name of the mechanism. That is important because this is going to give you credit in exam, right? Yep. And following which, we're going to start to generate the nucleophile CN minus. Yep. Now, just now I told you that the HCN, right, is the one that is giving you the CN minus. But unfortunately, I don't think that this is going to work purely. Why is that so?
Because HCN is a weak acid. It dissociates only partially. So the concentration of cyanide ions produced just based from the HCN is very low, that the reaction will not proceed at a significant rate.
Right. So what do you think that we can do to increase the concentration of CN minus then?
There's two strategies you can use. Firstly, we could add a strong base, NaOH, for example. Now, NaOH is going to react with the HCN to form the soluble NaCN salt, which dissociates fully to provide a higher concentration of the cyanide ions. Right. Alternatively, we could add some NaCN or KCN, which are all soluble salts. They will ionize fully once again to provide the CN minus ions. That's right.
So you saw that in the two equations that I wrote for step 1 over here. So depending on what is the original condition that you are writing for, you're going to write out the correct equation. Yep. Okay. Now, how about step 2, Mr. Yap?
Right. So the cyanide ion will then form a nucleophilic attack on the carbonyl carbon, which is electron deficient. Right. Right. So you see Mr. Leong labeling the partial charges. Right. So after it attacks the carbon, the pi bond will break, pushing the electrons to the O. So you will get this intermediate anion with the negative charge on the oxygen atom. Right. Okay. Now, that will be the slow step of this mechanism because out of the entire mechanism, this step has the largest activation energy. Right. Okay. Now, in the final step, this O minus anion is going to abstract a hydrogen ion from the HCN. Okay. This is known as an acid-base reaction, right, to form the final cyanohydrin, and the CN minus is regenerated. So the CN minus, since it's regenerated, we say it's a catalyst in this mechanism.
So in the second step of our nucleophilic addition mechanism, we saw that the CN minus, right, is attacking the electron-deficient carbon atom. Now, the special thing about this carbon, right, is that it is actually trigonal planar, which means that it is going to be flat on a piece of paper. So when the nucleophile comes into attack, there's two choices. It can either come in from the top and the bottom, and these will create two very similar looking products, right? Now, these two products, the way of the atoms they link together, they are exactly the same. The only difference is the fact that they are going to be mirror images of each other, right? So if you can follow me and draw a mirror line, you notice that the two products that you see over here, they are mirror images. Now, in the event that this final product is chiral, then these two have a very special name. What are these two pairs called?
Right, so if the resultant carbon is chiral, these two mirror images will be what we call enantiomers of each other.
right? What do you understand by enantiomers?
So enantiomers, basically, one enantiomer will rotate plane polarized light in a particular direction. The other enantiomer will rotate the plane polarized light in the opposite direction.
That's right. So in a game of the nucleophilic attack, right, it is actually a game of chance. You tell me that by probability, there'll be 50% of creating the product at the top, and there'll be 50% creating the product at the bottom. So once again, if they are enantiomers, you're going to see equal amounts of each enantiomer. Now, what kind of mixture is that called?
Right, this is what we call a racemic mixture.
Yes, a racemic mixture would have its optical activity cancel out, and as a result, you do not rotate plane polarized light.
Yep.
So this feature is very distinctive of nucleophilic add, and I hope that looking at this particular explanation, it triggers your memory a little bit from electrophilic addition as well as nucleophilic substitution, the first one, SN1, right? The reason why is because they all will end up with a racemic product mixture.
Wait, Mr. Leong, the only thing that you would trigger is bad memories for them whenever they study organic chemistry.
Okay, moving on. Yes.